And today we are going to discuss the linear momentum operator. The linear momentum operator. I request to the people, the students, to come earlier so that we can discuss a little more. Linear momentum operator. Look at these equations. The linear momentum operator, we are starting from the wave function of an electron. A wave function is actually the description of a system. The description means to define what it is. That is the description. You can see the wave function of an electron, psi is equal to a e power 2 pi I x by lambda, where lambda is the wavelength of the electron wave. Now, look here, when I differentiate this equation with respect to x, so d psi by dx is equal to, we are differentiating e power x. So, the 2 pi I by lambda, it comes here. A is not differentiated. And then e power 2 pi I x by lambda comes as such. So, this entire part is simply psi. This is an eigenvalue equation because e power x is an eigenfunction of d by dx. I have already told you what is an eigenfunction. So I can put a psi in the place of a e power 2 pi I x by lambda. So the equation becomes d psi by dx equal to 2 pi I by lambda into psi. So according to de Broglie wave equation, lambda is h by px, which is the momentum. The Planck's constant divided by momentum will give you wavelength of a matter, wavelength of a matter wave. So I'm going to substitute this value in the place of lambda. So px is going to the numerator, h comes to the denominator. So what I'm getting is d psi by dx is equal to 2 pi I x, sorry, 2 pi I by h px into psi. So I keep this px and psi in this place, and I'm transferring the 2 pi I by h to that side of the equation. So what I'm getting is a px psi is equal to h by 2 pi I d psi by dx. So px equal to, the psi can be neglected. So px operator is equal to plus or minus h by 2 pi I d by dx. The h by 2 pi can also be written as h cross. So it is h cross by I d by dx. This is the linear momentum operator. So linear momentum operator is h by 2 pi I d by dx. This is linear momentum operator. Now, so find the commutator of a position operator and a linear momentum operator. I've already told you what is a commutator. Commutator means if you change the sequence of operations, if you are getting the same value, that is A operator, B operator, f of x minus B operator, A operator, f of x, if it is equal to 0, then the operators A and B are commutators. Now we are going to find out the commutator of position operator and linear momentum operator. You know what is position operator? It is simply x Linear momentum operator h by 2 pi I d by dx. So let us assume a function f. Let us assume a function f. This function commutator is equal to, look here, h by 2 pi I can be taken out. So d by dx x f minus, I am changing the sequence of operation x first and then d by dx of f. So what happens? This becomes dx by dx f minus x into df by dx. So what I can do, this part dx by dx f plus keeping the f in the differential and x constant, x df by dx minus x df by dx. So this will get cancelled. So what you are getting is h by 2 pi I f. Actually, this part of differentiation is done according to this equation. D by dx of uv is equal to u into dv by dx plus v into du by dx. So this is the commutator value. As the value is not equal to 0, these two operations do not commute. Normally, in the Heisenberg's uncertainty principle, the two entities which cannot be determined simultaneously and accurately, their operators do not commute. This is called the quantum mechanical statement of Heisenberg's uncertainty principle. Any two operators do not commute if they could not be determined simultaneously and accurately. Now, look here, angular momentum operator. You know what is angular momentum? L angular momentum vector, L vector is equal to R vector into P vector. See, angular momentum is for a body rotating about an axis. Suppose this is an axis and the body is turning like this. Here it is linear momentum. This linear momentum multiplied by this radial vector, the radial vector, that will give you the angular momentum. See, I, j, k are unit vectors along x, y, z directions respectively. Then r vector can be written as I vector into x plus j vector into y plus k vector into z. Similarly, the momentum vector can be represented as I vector into px, j vector into py, k vector into pz. So L vector can also be written as I vector into Lx vector, j vector into Ly vector, k vector into Lz vector. So when you think of operator, this is only vector. When you think of operator, Lx operator, that is angular momentum along x direction, Lx operator is equal to, if it is a here x, you put y and z and then change z and y. So y into pz operator minus z into py operator. See, what is a pz operator? You know, because h by 2 pi I is the common factor into y dou by dou z. Actually, pz operator is h by 2 pi I dou by dou z. Dou by dou z minus z is here, then dou by dou y. Similarly, Ly, y, z, then x. So it is z into px operator minus x into pz operator. So h by 2 pi I z dou by dou x minus x into dou by dou z. Similarly, for Lz operator, z x y. See that cyclic change. X y z, y z x, z x y. Then you have to interchange y z, z y, z x, x z, y x y, y x. So it is h by 2 pi I x into dou by dou y minus y into dou by dou x. So the total angular momentum is L square is equal to Lx square plus Ly square plus Lz square. Similarly, L operator square is equal to Lx operator square, Ly operator square, and Lz operator square. Now, we are going to derive an equation for kinetic energy operator. Kinetic energy operator is E is equal to half mv square is the kinetic energy. So I multiply the numerator and the denominator by m. So what I am getting is m square v square by 2m. mv is the momentum p. So I can write p square by 2m. So what is p operator? It is h by 2 pi I d by dx. So what is p square? What is p square? P square is, I don't want the people to come late. So what is p square? P operator square is minus y minus because I square is minus 1, h square 4 pi square d square by dx square. And a 2m is introduced. So that will become 8. Actually, this 2m should not be written here. Yeah, I think px square. Yeah, 2m is introduced. So what happens? It becomes minus h square 8 pi square m d square by dx square. That is called kinetic energy operator. T operator is equal to minus h square 8 pi square m d square by dx square. So this is kinetic energy operator. Hamiltonian operator is a total energy operator. See, total energy is just the sum of kinetic energy and potential energy. Kinetic energy is T, potential energy is V. So total energy is H, which is called a Hamiltonian operator. So Hamiltonian operator is a total energy operator. H operator is equal to T operator plus V operator. So H operator is equal to T operator, you know, it is minus H square 8 pi square m d square by dx square. V operator is potential energy Vx operator. This is along x direction. Suppose if you want to write in all directions, instead of d square by dx square, write dou square by dou x square plus dou square by dou y square plus dou square by dou z square, and also V operator is taken in all the three directions. And this dou by dou x square plus dou by dou y square plus dou square by dou z square can be written as del square. This is del square. So Hamiltonian operator is a linear operator. So H operator psi will give you total energy into psi. This is an eigenvalue equation. So an operator is operating on a function and you are coming out with a coefficient and a function itself. This coefficient is called eigenvalue. So the eigenvalue of this equation is the total energy, where the operator is a total energy operator, where psi is the description of the system, which is the wave function. Or this can be expanded and can be written like this: T operator psi plus V operator psi is equal to E psi, where E is the value. Now, there is a condition called hermitian operator. What is a hermitian operator? An operator is said to be hermitian if it satisfies the following mathematical conditions. See, if this operator A is said to be hermitian, you integrate between the limits minus infinity to plus infinity. You first take the psi star, A operator, then phi in the volume element d tau. If you exchange the functions, look here, I have changed the functions. The phi is here, psi star is on the other side. And the A operator is also taken the complex conjugate. If these two integral values are equal, then the functions psi and phi in the small volume element d tau, the A operator is said to be Hermitian. So Hermitian operators have the following characteristics. Number one, their eigenvalues will be real, and also their eigenfunctions will be orthogonal to each other. So these two things we are going to prove, that the eigenvalues of a Hermitian operator are real, and also the eigenfunctions corresponding to different eigenvalues are orthogonal to each other. You know what is orthogonality? Their inner product will be zero. So these two things we are going to prove. Look here, show that if an operator is a Hermitian, it will have a real eigenvalues. This is what we are going to prove. Let me take an equation. A operator, it operates on a function psi. It is coming out with an eigenvalue A, then psi. And another equation, A operator star, psi star, which gives an eigenvalue A star. Now I am going to multiply first equation by psi star. First equation by psi star. A operator psi d tau is equal to, look here, integral psi operator psi star A operator psi d tau. So this can be written as A is a constant. A is a real value we are going to prove. So A can be taken out, integral psi star d tau. This is what we are getting. Similarly, I'm going to multiply the second equation by psi and integrate. What I'm getting is integral psi A operator star psi star d tau is equal to integral psi A star psi star d tau. This is here also you can take this A star out, and it is integral psi star d tau. So these values, see, integral psi star d tau and integral psi star d tau. Therefore, I can write integral minus infinity to plus infinity psi star A operator psi d tau is equal to integral psi A operator star psi star d tau according to Hermitian conditions. If this is satisfied, then only the operator is a Hermitian. So if these two things are equal, these two things supposed to be equal. So I am writing these two things are equal. So if these are equal, then the A star can be taken to the other side with a negative sign. I can write A minus A star in integral psi star d tau is equal to 0. Here, the psi star d tau has to be a finite value. It has to be a finite value. Therefore, this part cannot be 0. So what is 0 is A minus A star. If A minus A star is 0, then A and A star will be equal. If A star and A are equal, then A star is real. If it is a complex number, A star would have obtained a minus value, then this thing will not be true. Therefore, A is a true value. It is a real value. This is how it is proved. Now look here. I'm going to prove the functions are orthogonal. The same principle. Psi A star psi, sorry, A operator psi equal to A1 psi. A operator is operating on a phi star, which is equal to A2 star phi. I am taking these equations. As usual, I'm going to multiply the first equation with the phi star and integrate. It is phi star A operator psi d tau. This is equal to A1 can be taken out, integral phi star psi d tau. Similarly, I'm going to multiply second equation by phi star and integrate. So integral psi A operator star phi star d tau. Actually, here one star has to be there, equal to A2 star integral phi star psi d tau. So from the equations 3 and 4, A1 integral phi star psi d tau equal to A2 star integral phi star psi d tau. So similarly, this A1 and A2 can be taken to the other side because all these things, these two things are the same. So A1 minus A2 star integral phi star d tau is equal to 0. So now certainly A1 is not equal to A2 star. Therefore, this part cannot be 0. So this part is supposed to be 0. If integral psi phi star d tau is equal to 0, then the psi and the phi star are orthogonal to each other. This is how it is proved. So next. Now, we have to prove the linear momentum operator is a Hermitian. How to prove linear momentum operator is a Hermitian? Very simple. First, to take the linear momentum operator, then you integrate, you put a psi1 star and a psi2 dx. Let me say this is equation A. So in order to solve this equation, I am taking the formula integral u dv is equal to uv minus integral v du. So here u is a psi1 star, du is d psi1, so d psi2 by dx, du. So du is h by 2 pi I d by dx of psi2 dx. So what is u? You have to integrate h by 2 pi I d by dx of psi2 dx. So you are calculating what you are finding out what is u and what is v. So when you substitute here u into v, that is h by 2 pi I psi1 psi2 star between the limits minus infinity to plus infinity minus integral v du. V is psi2, du is d psi1 star dx into dx. So when you solve, it becomes minus h by 2 pi I integral minus infinity to plus infinity psi2 d psi1 star dx into dx. So what it becomes when you take the minus h by 2 pi I inside and put a whole star, what you are getting is this equation. When you compare A and B, it satisfies the Hermitian condition. See, psi1 star operator psi2 is equal to psi2 operator star the function. So this is satisfying the condition. Therefore, linear momentum operator. So linear momentum operator is Hermitian. Next, we have to prove similarly the angular momentum operator Hermitian. You just follow the procedure, the same procedure. You are starting with this equation. You are applying UV formula for integration, and then integral u dv is equal to uv minus integral v du. The same formula you are applying, and finally you are getting the same condition, that is a function with its complex conjugate, an operator, and another operation. You are getting operator star and the operations interchanged. So angular momentum operator is a Hermitian. You just work out as I have done, and if you come across any doubt, you please ask me. Now we are going to prove the Hamiltonian operator is a Hermitian. That is also the same procedure you do by yourself, and then come back to me if you have any doubt. Now the postulates of quantum mechanics. See, the first postulate, any system in the universe can be described as completely as possible by a function called wave function, which is a function of position and time. And then in the first postulate, you have to derive the linear momentum operator from the wave function of an electron. As usual, these are all already taught. And then you have to write the angular momentum operator, which is already discussed. And then you have to write the Hamiltonian operator. And the second postulate is A operator psi equal to A psi. The only possible values that can be observed of a physical property like angular momentum, energy of a system are the eigenvalues in the operator equation. See, this is second postulate. If an operator is operating on a function, what is coming out as an eigenfunction is the real physical entity which can be measured. Suppose if I take linear momentum operator what I'm getting is the measurable linear momentum. If I'm taking the kinetic energy operator, what is coming here is the kinetic energy. If I'm operating the potential energy operator, what I'm getting here is the potential energy. So these are all the physical, the eigenvalue is the physical entity which is measurable. That is second postulate. And this is a simple explanation for the eigenfunction. And the third one is the expectation value. An average value or the expectation value for an orthonormal function psi can be expressed as psi equal to summation of I phi I. So simply the same normalization procedure is explained. Now look here. This is a fourth postulate is the time dependent Schrodinger wave equation. So H operator psi equal to I H by 2 pi dou psi by dou t. I'm just deriving the time dependent Schrodinger wave equation. Psi is actually the function of a position and a time, which can be separated and written as a psi of position and the phi of time. Now, first, the psi is differentiated with respect to position. You are getting this, the equation. Then it is double differentiated. Then psi is differentiated with respect to time. And H operator, I am substituting minus h square by 8 pi square m d square psi by dq square plus v operator psi equal to e psi. Similarly, h psi equal to I h by 2 pi dou psi by dou t. This is time differentiation. This is position differentiation. So this is equal to I h by 2 pi 1 by phi dou phi by dou t. See, this particular part, this psi can be taken here, 1 by psi equal to E. Similarly, I h by 2 pi 1 by phi dou phi by dou t is equal to E. So I am writing this is E psi, this is E phi, where phi is a wave function A into e power 2 pi I et by h, and psi is a wave function A psi e power 2 pi I et by h. But psi equal to phi into psi. So this is how the equation is derived. Now there is another concept called the probability density, which is psi star. That much is enough for the undergraduates. So with this, we are completing the quantum mechanics also. I have completed the entire syllabus. So